Hi, this is Alex Yazdani. This is a demo video for the final project in EE533 in the spring of 2025 with Professor Young Cho. My lab partners are Szymon Gorski and Tim Liu. This is the 5th demo video, so not the final one yet, but our progress here is pretty good. We're implementing Dark Night, which is a technique for security that involves image obfuscation. So we're accelerating that process in hardware. And at its core, it's just multiply, accumulate, matrix multiplication. So first we implemented it in Verilog so we can do a simulation here. And we have a Python wrapper that basically calculates what the output matrix elements should be just in decimal. And then it converts the result of our Verilog simulation from binary into the actual decimal. And so if I run this, the average error is about 0.275%, which is pretty low. We have 512 outputs here. That's because the output matrix size is 512 because there are 8 images that are 8 by 8, so 64-bit. You can see that some of them say failure, but these aren't true failures. It's just marked to say failure for anything that has an error above 1%. But actually, when we decode the images, this error gets attenuated. So anyways, this is our kind of gold standard that we're measuring against. And we know that this is working, but it's our simulation. So we actually want it to work in hardware. So on the FPGA, we just download the bit file, line 5. It should only take a moment. And then load. So right now I'm loading the instruction memory. It's interleaved. It turns out that we needed to pipeline our floating point adder to meet timing. And so because of that, now the feedback loop spans 2 different stages instead of just one. So to accommodate for that, like every consecutive instruction that's dependent on the last needs an extra cycle of latency. And the most clever way to get around that is to just interleave instructions. So basically we generate a program and then we just cut it in half, and then we alternate between which half we're running at any given time. So now I'll load the batch data. And then we'll just load the scalar data. Oops, made a typo here. So yeah, then just for a sanity check, we want to check the output memory. And we expect nothing to be there right now. So yeah, it's all zeros. It's just uninitialized. But now if we run our pipeline and then stop and dump, we can see that it is outputting stuff, which is good. Now if we go up here and compare this to the dump of our simulation that we know has about a 0.275% error, we can see 40 DC, 3C55, 41 E7, and then let's check the top. B6, 2E, 3D, 3C, 3C, F9. So of course we only checked the very top and bottom, but if you do check this, it is exactly the same. So our hardware implementation is working as expected. Now if we want to decode, what we can do is just load the inverse matrix. And then I've already saved the output that we just looked at. So we want to load that encoded matrix back into DMEM. And I have that saved under batch 2. So we do that. Now before I run that on the FPGA, let's just run it over here. So to do that, instead of loading the scalar and the DMEM, we want to load the inverse scalar and the encoded into batch. So now Let's do that. It says failure, but this is just because it's comparing against the wrong thing in the Python file I was just using. So if we go over to the file %error, let's drag this over here. Let's run this. And now we can see that it has even a lower error, 0.1%, which is extremely low. Actually, with a resolution of 0 to 255 for any pixel value, there should be no errors. And that is what we see also. So you can see these values here are very good. So some of the larger errors that we saw before actually got attenuated out. And there's a good explanation for that, but I'll spare it for now. So let's go ahead and run that on the FPGA. And then dump dmem again. Now to pull that up, I just need data encoded. So we expect the bottom to be 3E1C, which it is, 3C5F, 3FDC. So that's right. Let's just check the top. Be 3D40, 3D4C, 3D38. So this is exactly the same. And again, if we pull this out and compare all of them, we'll see that they are the same. So that's where we're at for our hardware implementation as of right now. We're still trying to implement routing into all of this. So that's our next step before our final demo. And also in our final demo, we will be showing off like a scaled up version of this in software. So I have that right here. This is already working. The point is just we don't have quite the utilization on this FPGA to implement images at this scale, but it's definitely doable in hardware. So we're showing the software just to basically show that this is doable, and with more time and more funding, etc., we can do that. So first, let's run this. It pops up this window. So these are just 8 images. These are 1024 by 1024, and they're all color, which is great because we just split these up into their RGB, and then we can do the matrix masking on all 3 colors. So we have 7 images and then 1 noise image. Now let's X out of this. So first it will display the red channel, then green, and then blue. So it's actually splitting up the images into 3 different data sets so that it can process each one. So then after it does the masking, these are the encoded images, and if you look closely, you can still make out some stuff, but it's encoded pretty well. We actually found a way to improve the encoding quite a bit since last time, as it was a little too easy to see. Now I'll quit out of that, and this is the decoded data, and this is actually the decoded data. This isn't just plotting the original image set from before. This is it did the matrix multiplication to obfuscate the images, and then it multiplied the inverse to recover them. And yeah, so that's about it. So thank you.